Okay, so I guess we're ready to get started. So thanks everyone for joining us for the penultimate working group on active B-stars seminar of the academic year. I know this is a busy time in the semester, a lot of finals approaching, so I appreciate you taking the time. And of course, this talk will be available on YouTube afterwards. So today it's my pleasure to welcome Matheus Bernini Peron from the University of Heidelberg. Matheus is currently a PhD student there and previously did his bachelor and master's at the Federal University of Rio de Janeiro. And so Matheus today will be talking to us about the hypergiants. So without further ado, Matheus, please take it away.
Yeah, hi everyone. Good morning for you, I guess, for most of you probably. Yeah, first of all, thanks Alex for inviting me for giving this talk here. It's always nice to share and have discussions. Even even if it's not the core theme of my presentation, but anyways, I'm talking about a specific type of B star, so I guess it also fits. So yeah, looking forward to share these with you and also for your questions and discussions. By the way, feel very free to interrupt me anytime and simply unmute yourself and jump in to make questions if you wish. It's no problem at all. Yeah, Alex introduced me already, so I don't need to do this. Thank you. So yeah, then let's go and talk about B-hypergiants. So this presentation, it will be heavily based on, like, the scientific content will be heavily based on my most recent paper, which is just available in archive since a few weeks ago, which is essentially discussing the hydrodynamic modeling of the atmosphere of these stars. And yeah, so since we all here study B-stars, I want to start with some sort of context explaining what it exactly is a B-hypergiant. So starting from a very innocent B-giant, I'm just showing here the spectral features of which are very characteristic of B-stars in general, the strong Balmer lines, helium lines, magnesium, silicon, and some CNO here, CNO, for instance, nitrogen, which is seen in basically most B-stars in general. But this is a giant. Now, if I take a supergiant with a similar effective temperature, we start to see that like the Balmer lines, they start to get narrower, and H alpha, for instance, can start to get in emission or in P Cygni, and yeah, other lines basically still behave the same. And if I keep going this increasing in the luminosity class, and take here, for instance, now B-hypergiants, then we start to see that even further orders of the Balmer series start to get in emission or in P Cygni as well, for instance, H beta. And if I take other B-hypergiants as an example, even H gamma and then H delta, and even helium start to have some sort of a winged P Cygni component. And for some objects in particular, the winged helium features also start to get stronger, and even metal lines also start to become with these very characteristic P Cygni profiles, which here I'm showing exactly a very special B-hypergiant, which is the P Cygni star itself, which is also an LBV. Yeah, so essentially this illustrates what means for a star to be a hypergiant. It's essentially a spectroscopic classification in which the Balmer lines from H beta and bluer stars to get in emission or in P Cygni. And here I'm just showing some stars which I showed before, in comparison. And this spectroscopic characteristic of having H beta in emission is something that we also observe in a very also special type of stars, which are the so-called slash stars because they are OF/WN stars, where we also see H beta and even some other lines in Balmer lines and even helium lines as an emission or in P Cygni as well. And these stars, they sit right in between the normal O stars and WN Wolf-Rayet stars, which is basically something similar to what happens to B-hypergiants. We have here the normal B supergiant and the regime of the LBV stars. So both share these sort of in-between characteristics. However, the slash stars, they are much hotter, like 50, 60,000 Kelvin, while the B-hypergiants tend to be much cooler, like they are B stars after all. And also other informations in general about the B-hypergiants is that they are quite rare objects. So in the local group, as far as I could count in the literature, less than 40 are known or identified, despite they being so luminous. Also, they apparently have a low binary diffraction, but this could also be a bias because of their high luminosity. And very, very rarely they are earlier than spectral type B1. There are maybe like one or two, which are like B0.5, 1A+, and also O hypergiant as well. And also another, like the fact that they are luminous makes them also being quite approaching. Some of them are really close to the Humphrey-Davidson limit, which might reveal that they are also quite close to the Eddington limit. However, as you can see, they span a quite wide range of luminosities as well. And some of them are known to be related to like LBVs. Like by that I mean that some of them really show signatures of LBV activity in their past. And precisely these like properties, even as you can see here in the HR diagram between the B stars and the LBV regime, and even touching the Wolf-Rayet regime, the fact that they have these in-between properties make them really valuable for us to prove and study massive stellar evolution. Also, and these sort of in-between properties, they also show up in their winds. If you plot the mass loss rates against their terminal velocity, here we have most of the B supergiants and all stars as well. And here we have WN and so Wolf-Rayet and LBV stars. And you see that the B-hypergiants, they populate right here in between, almost like bridging these two groups, which also is quite interesting and important for us to understand the physics driving and shaping the winds of this object. And this also is very well reflected in their spectrum. As I mentioned, they have P Cygni profiles and also normal photospheric lines, which shows that their atmospheres have these very unique and special characteristics of the wind. It's starting to get sort of dense enough to show off and contaminate some photospheric lines. This is great for us to study the physics behind the line-driven wind towards cooler temperatures, like the B-star regime. However, this is also very challenging for us to model and reproduce. So that said, that's the context. The aim of our work is then essentially to take hydrodynamically consistent atmosphere code, thereby performing a quantitative spectroscopy to analyze the winds of early-type B-hypergiants. More specifically, but when I say early-type B-hypergiants, I mean spectral type around B1, B1.5, since they very rarely are earlier than that. Okay, and what I mean by exactly quantitative spectroscopy or stellar atmosphere codes. So essentially, are programs in where we just put the input physics, so luminosity, temperature, chemical composition, abundance, etc., the atomic data for us to account for all the transitions, since we are working at non-LTE, since it's hot atmospheres, and also you provide the wind velocity structure. But keep this in mind because this will be important later. Then the code will solve the rate equations and the radiative transfer. And then after some time, you have the atmosphere structure with all of your like density profile, temperature profile, ionization stages, and the final synthetic spectrum. And if this synthetic spectrum matches what you observe in real life, then you can say that your input properties reflect well the reality. So this is the traditional stellar quantitative spectroscopy. But now we are working with a sort of a updated version of that, because before we were giving the velocity structure as an input. So we just assumed certain velocity, certain behavior for the velocity, and we provide that to the code, and the code would essentially compute the atmosphere from that. Now, the velocity structure is a consequence, should be iterated, and is shaped also by the radiative transfer and the ionization and excitation levels of the atoms. So it's also part of this iterative consistent loop aiming to reach self-consistent solution. And by doing this, the mass loss and terminal velocity are no longer inputs that you give, but an output. So it's something that you obtain as a result. So if in that framework, if we really match what we observe, this means that the physical parameter that we put, so temperature, luminosity, they are probably representing much better than the reality than in the case before, by assuming certain velocity structure. Yeah, okay. So just a quick break for me to drink some water. If it's not clear, something, please interrupt at any time. Right. Are the slides frozen for you?
Yes.
Yes.
Wait. Oops. Let's try again. Oh, it went much ahead. Okay. Now it's moving normally. Is it moving okay for you now?
It seems to be back. Oh, now it's moving. It's very slow,
Okay.
I guess.
Yeah, old laptop. Yeah. So this the flow of work of the framework that we are using, and just showing this more in practice. What does that really means to be a self-consistent solution in terms of the hydrodynamic? Here I'm showing the acceleration of the wind different types of acceleration against some arbitrary units for the atmosphere. So here is outside, so sort of infinite already outer space, and here is the interior of the star, or at least the inner layers of the envelope. It doesn't go down to the stellar structure. And here just showing different types of accelerations. So for instance, the Thomson acceleration here in green, continuum acceleration in purple, pink, and the total radiative acceleration is this this thick blue line, and the provided like structure given by the user is given here as this white thick line, which is also called the total mechanical acceleration, which combines the advection term and the gravity. So as you can see, both of these two curves, they're different because the radiative acceleration is not imprinting its the radiative acceleration is not imprinting its shape into the total mechanical acceleration in the wind, and the radiative acceleration is computed from the flux and the opacity, and also here's accounting for the pressure terms, which depends on the temperature, which also depends on the transition and population equation, and population of the different ions and excitation stages of the atoms. So it's a very intricate problem where everything is coupled and should be solved simultaneously. But now, when we take the hydrodynamically consistent models, these curves now, by design, they will adjust each other until they match. So the radiative plus pressure term should be equals to the mechanical terms, so the inertia, advection, and gravity, therefore satisfying the equation of momentum, which is essentially Newton's second law. So hope this illustrates well what this means to be a hydrodynamically consistent model. And basically we took this principle and we applied to model a very prototypical B-hypergiant in our galaxy, which is Zeta 1 Scorpion. And we chose this star because it's a very bright object and therefore has a very nice spectral coverage from the far ultraviolet to the mid-infrared. So we can really take our model and put it to the test in multiple wind diagnostic regimes, not just wind diagnostics, but also photospheric as well. So from the far UV, which will trace wind properties, up to near UV, optical, and mid-infrared. So starting with the ultraviolet, I won't go through the details of each line fitting. So the focus here is just to show you that the model is reproducing all of the lines, and at least qualitatively. Of course, there's some overestimation in some parts, some underestimation for other profiles, but the general idea is to get the gist, so reproduce the main characteristics of Zeta 1 Scorpion, this prototypical hypergiant. And here, since you're talking about the ultraviolet, I also used the opportunity to talk about some previous works that I did in B-hypergiant, because here you can see that this star has nitrogen 5 and carbon 4. And this star has a temperature of about 18,000 Kelvin, which is very cool, very cold for these lines to appear naturally. Therefore, the star also has superionization. And and one of the the things I did in my master's and also earlier stages of my PhD was precisely investigate the superionization in B supergiants. Not exactly the same type of stars, but related. So in cool B supergiants, previous modeling, spectroscopy modeling could not reproduce these lines. So like for instance, carbon-4, they were not reproduced. But then when we took similar models and included X-rays, then we could reproduce these profiles much better. So we needed to add X-rays as an additional source of ionization. And we did this for galactic stars and also for a big sample in the Small Magellanic Cloud. So we see that this also does not seem to depend a lot on metallicity. But what all of this reveal is that the atmosphere of B supergiants, even at cooler temperature, like 16, 17,000 Kelvin, they have X-rays and they can create this superionization. And this is exactly what we are seeing in this B-hypergiant as well. Of course, it behaves in a different way because B-hypergiants are not exactly B-supergiant when you really look into their atmosphere. They have much higher Maslow's rates and wind density, but it's interesting that this effect is right there as well. So closing this parenthesis, we can go to the optical regime, where our model is also reproducing, well, most of the lines and profiles. Here just showing a few examples. So it's getting silicon-4, silicon-3, like also helium as a P Cygni profile, and so on. Of course, some of them are not properly reproduced, but then we also didn't fiddled and fine-tuned for the abundances, for instance. But the main point is that we are reproducing these lines, and therefore our predicted stellar atmosphere structures is likely representing relatively well the reality. And also in the infrared, just to show you that it's also, the models are also reproducing the features. Yeah, so having that confidence that our model is similar to what is observed in real life, we then have confidence to really go in depth to see what's going on in the wind of these objects. And the first thing which I took a look was exactly the wind driving, which is the main point of this work. And not surprisingly, actually, we already sort of expected that the wind of this object is basically ubiquitously to a most extent led by iron 3, which is also observed in B supergiant as well. And you see here the iron 3 is this blue curve, and yeah, iron 2 and iron 4, they really don't contribute much. And here in the critical point of the wind, which is this point is where is essentially where you are transitioning from the subsonic to the supersonic. So in the from the photosphere, surface photosphere, to the wind regime. Here is also iron 3 is the dominant ion, iron 3, and the acceleration from the electron scattering. Yeah, by the way, here I didn't explain the units, that here this gamma is essentially acceleration divided by gravity, plotted against the stellar radius in some convenient units to really give a zoom in this part. So here's inside the star and here's outside the star. And here is just the radius where I turned on the X-rays to have a better reproduction of the UV spectrum. And when we compare with other elements as well, so here is just different ionization levels of iron, and here I'm plotting a lot of different metals. So don't try to follow all the lines. They are not really important individually, but this is just to show that iron 3 dominates really dominates much more than the other metals combined also. Maybe not here in the upper part where the X-rays really kick in and increase, make that nitrogen 5 and carbon 4 and some other ions which are sensitive and affected by X-rays much more. They start to have a larger imprint in the wind acceleration. But the main message is that iron 3 is the biggest contributor. Yeah, okay. And after understanding how the wind is accelerated and launched, we look at the velocity structure that this acceleration produced. Here, I'm again showing our hydrodynamically consistent model, here showing the velocity against the logarithmic of the radius. And here, this blue vertical line is the critical point, and this is just a zoom in of this part. So the first thing that we notice is that this acceleration profile seems very shallow. Like the acceleration, you see that the acceleration, the gradient of this curve seems very shallow. So the slope is not big. So the wind does not accelerate fast. As actually we have seen here that it stays close to the gravity for a big part of the wind. So it's a wind that accelerates really slowly. And this shallow gradient, when we translate to a more traditional as stellar spectroscopic modeling, and also taking back to the more primordials of the radiative-driven theories, the CAK theories, this corresponds to high beta values. So which beta is the parameter which controls how much an input acceleration profile would be or wouldn't be shallow or have a sharp curve here. And this is what I'm illustrating here. Like I took this hydrodynamically consistent model and I plotted theoretical beta values, and saw which one would fit better our model. And we found that was something around 3.3, so a very high values. Usually typical values for OB stars are between 1 and 2.5, something like this. And then having determined this value, this best value, 3.3, in comparison to the hydrodynamic consistent models, I created a normal traditional model, not hydrodynamic consistent, and with a velocity profile with beta 3.3, which are the green and the red curves. And here you see that they actually match quite well, at least the red curve. So yeah, it reveals that, okay, in the inner part, this setting seems to reproduce well what a consistent modeling predicts. And the green, here you see that they don't match really well. And what exactly is the difference between the red and the green? Because all of them, both the blue, red, and green, have the same stellar properties, but the red and the green also have the same beta values. However, they have a different settings of connection between the photosphere, the inner part of the wind, and the outer part of the wind. Here, I'm showing the gradient of the velocity against the radius. And here, the blue again is the hydrodynamically consistent model, and the red is the model which matches nicely here. And you see that both the hydrodynamically consistent model and the model with the red curve, they have this sort of sharp transition and this double bump structure, which is something that seems to be characteristic of a B-hypergiant. And you see that a smooth connection, therefore forcing that the gradient of the velocity profile, the velocity profile in the photosphere and in the outer wind, they should connect continuously. They don't really match well. And also when we compare the spectrum, the red and the blue, they have a very similar spectrum. So this sort of double bump structure in the gradient of the velocity is important for reproducing the spectrum of B-hypergiants and their stellar structure in general. Yeah, so this is about the velocity, and now we can move to another thing, a very important aspect, which is clumping, which also touch the mass loss that we infer for the star. Yeah. So clumping, just to give you a context, is essentially a measurement, a way to try to quantify how inhomogeneities in the outflow of the wind. So yeah, a wind with high clumping would be outflow which is full of inhomogeneity, so over densities and under densities. And of course, nature is three-dimensional. Since we work with one-dimensional codes, 1D codes, it's important to find ways to parameterize this. And yeah, in the approach which we are using, we are parameterizing the clumping as a sort of a filling factor parameter, which essentially will dictate how much the wind would be smooth or not, which then have several effects on recombination lines and the ionization structure in the wind. And this parameter here, as we implemented, they are following the very used called Hidi exponential law, which is used in a lot of stellar quantitative spectroscopy analysis. And so essentially the clumping here is a function of the velocity sorry, there's something appeared here. Okay, yeah, so clumping is essentially a function of the velocity in the wind. Here I'm showing this clumping parameter, this volume filling factor. So 1 means a completely smooth wind, and tending to 0 would be a very clumped wind, so a very inhomogeneous outflow. And here I'm showing the corresponding spectrum of this structure. And here I'm showing some stellar, some wind properties, so the mass loss rate and the terminal velocity. Here, this diamond indicates where is the critical point. So that point where the mass loss rate is settled in a hydrodynamically consistent model. And here the star represents the optical depth of the photosphere. Yeah, optical depth, which is here the x-axis. So here is the inner part of the atmosphere, and here is outwards infinite at space. So we see here that a model without clumping don't reproduce well the observations in gray. You see that it looks like something, just an absorption profile without this characteristic P Cygni profile of a B-hypergiant. Then we try different values of clumping. So here is we try different onsets of clumping. Here, all of them have the same amount of clumping. So this F parameter, the value that we set to be in the outer part of the wind is the same for all of them, for all these two. But where the profile starts to go towards this value changes. So here, this characteristic onset velocity is 30 kilometers per second. So further out in the wind. And here, you see that it's essentially the same as a model without clumping. And this happens because here at the critical point, the value of clumping is still like 0.85, which is still very close to 1. However, when we put like when you force clumping to start at deeper layers, therefore at lower velocities, and then we have that at the critical radius, the value of clumping is already almost the maximum that we have set. And then finally we can reproduce the spectral line as a P Cygni profile. This is just one example of one line, but of course we look to many diagnostics throughout the whole spectrum. And here you can really see also that the mass loss rates, they change quite a lot when we change clumping. So from -6 to -5.6, so almost 1 order of magnitude. And the terminal velocity, they don't change much, but because they also depend on what's happening in the outer part of the wings. And yeah, so we did this test to sort of know where we could start having the clumping properties. So where we can start, we can make clumping, where we could make clumping start in the wind, which was very close to the photosphere. So really at sub-photospheric velocities. And now we investigate how much how much of clumping we really need in the wind. So how much inhomogeneous this outflow can be or can be not. So we took our best model, which had a clumping value of 0.7, something like this, and an output mass loss rate. Here I'm plotting this clumping, the maximum clumping parameter against mass loss rates, the output mass loss rates from our models, and then we just vary the clumping. We took the same model and kept the properties, just varying this clumping parameter. And we noticed that when we put this clumping parameter to lower values, we start to get lower mass loss rates. So basically almost an order of magnitude. But when we did the other way around, then we start to see the reverse effect of a much higher increase in the mass loss rates, also to almost an order of magnitude. And this effect is also something which is kind of expected, like by previous studies. We know that the increasing of clumping, especially at the critical point, causes an enhancement of the opacity at that region, and therefore you have more radiation which is sort of trapped in this part. Therefore, these photons will transfer more momentum. Therefore, they can sort of push more matter to produce stronger winds, so a more dense wind. And and of course, with higher mass loss rates, we also start to see a very clear effect in the spectrum. So here, each spectrum follows the same color coding here. So models with higher mass loss rates will have a much stronger emission or P Cygni profiles than models with lower clumping. So more smooth wind. Here you see that they become essentially photospheric. And when we look at the terminal velocity, we see sort of a more complicated behavior, so the terminal velocity don't vary so linearly with clumping. And in this regime, actually, it's actually something very counterintuitive, because you would expect that a denser wind would be slower. However, in this sort of in-between regime, so between a very clumped wind and a very smooth wind, both mass loss rates and terminal velocity, they increase equally in that regard. Yeah. And now returning to something which I mentioned in the earlier in the talk, that B-hypergiants and these slash stars, they show these spectroscopic similarities. And therefore the B-hypergiant could be thought as some sort of cooler counterparts of these stars. However, one very particular characteristics of these slash stars is that they seem to be quite close to this sort of transition regime between thin winds and really becoming more thick winds, which is translated by this wind efficiency parameter, which was introduced by Vic and Greffner in 2012, which is essentially the combination of mass loss, velocity, and luminosity, which if it's equal to 1, and so all the mechanical momentum is similar to the radiative imprinted momentum. If this happens, and the optical depth at the critical radius is also close to 1, then you really get into a much denser wind regime, so close to what is seen in Wolf-Rayet. However, when we did this test for B-hypergiant, for our B-hypergiant, we got a value which is very, very far from 1, so 0.1, so 10% of what is required to go to be considered a transition star in this transition wind regime. And by varying the clumping parameter, the x-axis is again this clumping parameter, even when going to higher clumping, so increasing mass loss rates up to its maximum, as far as we could, at least as far as we could obtain as output, we also couldn't approach 1. And it's interesting because even the optical and the many other parts of the spectrum are really popping up in P Cygni and emission. So the spectrum has full of these emission and P Cygni lines, but the star is still not really doesn't have a still thick enough wind to really be approaching what is seen in Wolf-Rayet and what is at least inferred for Wolf-Rayet and even some LBVs. So this reveals that at the cooler temperatures, the spectrum can be much more dramatic, full of P Cygni and emission lines, but the wind is still not that thick as it happens for a hotter wind regime. So so this also shows that B-hypergiant are maybe from a not so well related to the slash stars. And then finally, as a sort of a wrap up for like going to computing the mass loss rates. So these are the mass loss rates that we obtain, and these really they are really similar, like in general, sort of similar order of magnitude of what is obtained or at least inferred by other studies which use different techniques. So quantitative spectroscopy, but not hydrodynamic consistent, and from infrared SED analysis. And you see that it is sort of a similar order of magnitude, but it's still different. However, when we, here should be m dot, not n, sorry. But when we correct for the effect of clumping, because usually mass loss rates and clumping are related by the square root of this clumping parameter. So a model with a higher clumping in a traditional modeling would be equivalent of reducing the mass loss rate and still preserve roughly the same spectral lines. And you see that when you correct for clumping, we get an even more similar result. So this also revealed that yeah, that our modeling, our hydrodynamically consistent modeling is also it's coherent with what is have been inferred for the star for decades. Yeah. And then we compared the mass loss rate that we obtained against the mass loss rates recipe that we see that we have available in the literature. By mass loss rate recipes, I mean these really like functions that give you the mass loss rate as an output of the stellar properties for stellar evolution models. And yeah, the standard nowadays is the Vink mass loss rate. And when we put the our stellar properties into the to the Vink rate, then then we obtain a much higher mass loss rate than what our models predict and validated by the spectral fits. But when we compare to other more newer mass loss rates recipes, which imply a different evolutionary behavior compared to Vinks, then we obtain the inverse. We obtain underestimation. So it's interesting that we are finding something in between these two types of recipes, the old and the new ones. And then wrapping up, just to mention that all of this was for one star, but we are also working on getting the spectral fit, the spectral modeling of other B-hypergiants as well. They are also we are also trying to fit, which is not a simple process. Also including different metallicities and even higher at more extreme regimes such as P Cygni and other LBVs. And then we also are testing different with these models. These models, they're really versatile and powerful because we can really test how different parameters will impact our different parameters of the star will impact our final wind properties. And here I'm testing metallicities. So I took a model of a more extreme B-hypergiants, and then I changed the metallicity to see how it's behaving. And then we see that it starts to resemble more of a supergiant. So at maybe lower metallicity, certain stellar properties would produce a B supergiant spectrum instead of a LBV or a B-hypergiant. But these all work in progress, and stay tuned because probably will be my next paper. And here, I guess the time is about to end, so I leave you with the conclusions. Essentially, that we have now, for the first time, consistent model of a hypergiant, and all the structures and behavior that we inferred for the winds, and also that the hypergiants, they are not really a transition type to more dense winds such as Ofpe is, just like the OF/stars. So that's it. Thanks a lot, and looking forward for questions and discussions.
All right, let's thank Matheus for a very nice talk. Sorry, I was a bit frozen there. Thank you very much, Matheus. So we have some time for questions. If anyone has a question they'd like to ask. So maybe I'll use my prerogative and start. So that's a really nice, very thorough work. But of course, there's a lot of different parameters that come into play. So one thing I'm a little bit curious is, so either, I don't know for the star Z1 SCO or some of the others that you're currently working on, are there any kind of diagnostics that are available that are less sensitive to clumping, like X-rays or something that you can then compare to kind of benchmark your clumping determinations?
Well, in principle, lines which would be formed more deeper in the photosphere, they wouldn't be that much affected. But then also they wouldn't also be affected by X-rays, because actually, so I'll go to another path of explanation, that X-rays, at least in these objects, seem to be quite further out in the atmosphere, which makes sense because the wind is very slow, and at least as far as we know, like in the inner layers of the atmosphere, there wouldn't be enough energy even to produce X-rays, unless there are some other mechanisms that we are not aware of. But clumping itself, in principle, could start at very deep layers. And therefore they could impact much more the structure, and therefore the spectrum. But yeah, certain lines, at least which I've noticed here, yes, try to model zeta-1 scorpions, like deep lines which are formed deeper in the atmosphere, such as maybe silicon, so like silicon 3, silicon 4, they were not so much affected, or magnesium. But there's a problem, like not a problem, but like there's a catch, because when you also change in clumping, you also change a bit the whole atmosphere structure will adjust, and therefore the temperature of your photosphere will also change a bit. So, and these lines, they are affected by temperature. So they wouldn't be like directly sensitive to clumping, but they would be indirectly affected by it. So it's really like it's a problem where you really need to see the whole final solution before really pinpoint these lines affected by this, other not so much.
Great, thanks. I do have a second question, but I'll defer to Dietrich first.
Well, Alexander, go ahead, please. I can wait. Thank you.
Oh, so I was just going to say, do you have, among the stars that you're studying, stars for which you have kind of different epochs of observations? Because we know, of course, that when you look at snapshot observations and do these kinds of determinations, you might get different answers if you look at different observations. So how robust would you say your models are to that? And is that something that you've actually kind of considered and tested?
Yeah, I don't think I put in the presentation, but yeah, we looked at all the spectrum available in the ESO archive for this star, like different wavelength regimes. And yeah, our model also, like, we tried to get a model that was sort of resembling also the spectrum in different epochs. Also, that's why was one of the reasons for us not to be super nitpicky about it's fitting exactly this line in this spectrum. But then when you look at the spectrum of a certain epoch, you see the line change a little bit. So qualitatively, everything was similar. So like H beta had the same shape, at least similar shape, but maybe weaker, maybe stronger. And then you try to get a model that's okay to reproduce sort of the average of this.
Great, thank you. Dietrich?
Yeah, thank you. First of all, congratulations on very clear, very nice slides. Very well done. Many of these superluminous stars are suspected to be pulsating. And when you look at your numerical experiments, would you see an incentive to include mechanical driving due to pulsations, for instance, as something that could lay the route for the clumping?
Well, I don't know if we could directly test this, because these codes, they are time independent. So
Sure.
the solution is stationary. So therefore, yeah, we couldn't test exactly pulsations or changing properties with time. But yeah,
But you could introduce different snapshots.
Yeah, in principle, could be a study on its own that we would try really to model different epochs and see if there's like some evidence of pulsation. But yeah, it's not really also my area, so I wouldn't know exactly how to test pulsations in using different diagnostics, for instance. I don't know if it's related, but like I also checked for like radial shifts in the lines, mostly concerned about like binarity, but I didn't see anything. But I don't know if they could also trace pulsations. So could they trace somehow? But then, yeah, I also wouldn't know if these two would be the most adequate for that, to try to see pulsations and yeah, see and try to model the impact of it. But in principle, yeah, could be an explanation for clumping inside. Also, there's a lot of discussions of could be some sort of convective layers like inside, because also 3D simulations also predict some sort of radiative convection happening in the inner layers. So seems to be there could be like a lot of paths to explain this.
Yeah, I mean, you mentioned the radial velocity variations. The amplitudes are small, just a few kilometers per second. In HD 168625 in the LMC, the pulsations seem to be leading to shocks in the atmosphere. And that would then suggest that there is some mechanical driving of mass loss. Whether these pulsations, and this was detected during outbursts of that star, whether the pulsations are part of the reason for the outburst, and that these pulsations are detectable or have a significant amplitude only during the outburst, is something that would still need to be done. But it's worthwhile thinking about, I believe. Thank you very much for your answer.
Yeah, thank you. Actually, then I also have a question. So this star, is it like what the spectral type is also like a B star?
No, it's a sorry, I didn't say this. It's a luminous blue variable, LBV.
Okay.
At the time of its outburst, it was the brightest star in the LMC.
Wow, cool. Yeah, good to know.
So what was the data set that observationally showed those pulsations?
Say it again, please.
Well, what was the data set that showed the observations of the star pulsating?
These were radial velocity variations, and the line profiles, the profiles of some of the lines were split, and that was something we have taken as evidence of shocks.
It sounds maybe like
sorry. I forget the year of the paper, but the lead author was Andrea Mehner.
Oh, yes.
Mehner.
Thank you.
So I was just going to mention, it sounds like maybe, Matheus, once you have a larger sample analyzed, looking at some association between the clumping parameters you get and pulsation amplitudes, if any are detected, could be an interesting thing to look at. Okay, any more questions? I see we're slightly past the hour, but this is a very interesting topic, so we might have time for one or two more. Matheus, if you're still available, I don't want to put any strain on your time, but do we still have time for one or two questions, if any? Okay, in that case, let's thank Matheus again for a very nice and comprehensive talk, and we'll be convening for one last time before the Northern Hemisphere summer next month. The details should be announced shortly, so thanks again for attending. A reminder that this talk, as well as all of the others, are available on YouTube for your viewing pleasure, and please feel free to share with colleagues. And otherwise, thanks again, Matheus, and I hope everyone has a good rest of your day.
Yeah, thank you a lot. Thank you, Alex, and thank you all for coming. Thanks for the discussion also. Bye.
Bye, everyone.